Three-phase power. In this presentation, we're going to look at the relationship of electrical power in a three-phase system, as well as some of the more common calculations that we will have to execute. The first place we're going to start is with a basic review of some of the different types of power that we have in electrical and what those basic single-phase calculation or equations are. First one we start with is true power. It is also known as resistive power or the effective power. It's symbolized with P in equations and it's measured in watts. Below you can see four different calculations that we could use in order to come out with power in an AC circuit. To apply that, we could apply any one of those with 240, 5 amps, and a power factor of 0.6. I'm choosing to use this equation here, E total times I total times power factor, which immediately gives me 720 watts. Now, of course, this would be present on the horizontal portion of a power triangle, with the power factor being the angle or cosine of the angle in between the S and the P. Well, let's take a look at another one. The next one we're going to look at is called reactive power. Reactive power is distinguished by the symbol Q. It's measured in VARs, and it is the type of power that we have from inductors or capacitors. It is the store and release of energy at different points within the sine wave. Again, there are four different calculations that we can use in order to find Q or VARs of a circuit. If we use the exact same example, where we have our 240 volt, 5 amp, and 0.6 power factor, we should be able to come out with the VARs immediately with one equation. So what I'm using is the 240 times 5 times sine of the angle, and I chose to do that. I needed to convert my power factor out of cosine and back to its original angle form, and that required me to apply cos in -1 or inverse cos in my calculator. And then I took 240 times 5 times sine 53.13 degrees, and we get 959.99 var, which would be on the vertical portion of my power triangle. Again, my power factor in the middle, representing the relationship between the power and the S. And that would be all that we could do with the reactive value. Now let's take a look at the final type of power that we have, and this one is apparent power. Apparent power is the combination of all of those previous two types of power, capacitive uh, VARs, inductive VARs, and resistive watts. It's symbolized with an S, measured in VA, and there are only three calculations that we can use in order to get this value, not four. And that's because, well, if you take the volts and the amps in an AC circuit, your immediate value is then VA. So we come out with 1200 VA. And the VA would then be represented here on the hypotenuse or S side of my power triangle. Now, did I have to go through the preceding three calculations? Did I have to do that calculation for each one? Or could I have simply calculated one of them and used a little bit of basic trig and maybe Pythagoras to get the other two? And the answer is yes, of course. And when we're dealing with these types of equations and questions, there will be multiple ways that we can come to an answer where they're all going to be correct. So just bear that in mind as you progress through the course. There will be more than one method in order for us to come to a correct answer. So let's review the relationship now with different types of power in a circuit. So here I have three 100 watt, 100 volt resistors. They're connected in series to a 300 volt single phase source. And that means that each one is getting its rated voltage of 100 volts because they're equal in ohmic value, which means the voltage will divide equally across each resistor. In a series circuit, P total is equal to P1 plus P2 plus P3, giving me a total power of 300 watts. If we then apply the same logic, let's say we have three, again, 100 volt, 100-watt resistors in a single-phase system to a 100-volt source, now they're all in parallel, meaning each one will again get its rated voltage of 100 volts, meaning each one will still generate 100 watts of power. In parallel, the power relationship is P1 plus P2 plus P3. So again, we have 300 watts. Now let's take a look at a system that's three-phase. I now have three individual 100-volt rated 100-watt resistors. They're connected in Y, and I've connected them to a three-phase source that's 173 volts line to line. Now, each one of these is getting its rated voltage of 100 volts because it's in the phase. And because of that, the power relationship remains consistent. P1 plus P2 plus P3 equals 300 watts. And so this is an important step or factor to keep in mind, is that it does not matter how we choose to connect them, the power relationship remains the same in that like power values will always add together. So let's take a look at a few additional examples where this takes place. So like power types add together. And while my example was only in watts and all exactly the same wattage of resistor, it's also true with different sizes of resistors with different values of watts. In this installation, we have three different sized wattage resistors for a total power of 140 watts. In this one, they're all inductors, different size inductors. We simply add them together, 130 watts. This one is a mixed bag. It has a capacitor, an inductor, and a resistor. And we know that that means we're going to have some canceling of VAR values. So I've done a very basic calculation here to say 30 minus 20. Those are going to cancel each other, leaving us a remainder of 10 VARs of reactive power. And I can then use Pythagoras in order to calculate the VA with a power triangle. And here's the last one, two resistors and an inductor. Well, we add the two power values together to get 27 watts. The VARs is 60, and we can use a power triangle with Pythagoras to determine the S, or hypotenuse value, of 65.79 VA. Now, that was a Y system. What about a delta system? Well, you'll be happy to know that the logic doesn't change at all. Now, we are not going to be focusing on delta systems that are unbalanced, but it's still important to see the relationship. So here is exactly the same situation where we have a 60, 50, and 30-watt resistor connected in delta to a voltage that is appropriate for those ratings, and we get 140 watts. And here's again a delta inductor installation with three different values of inductors. Add them together and we get 130 VAR. This is one with resistor, inductor, and capacitor. In same sequence, we would have to subtract the capacitive and inductive VARs to determine what the remaining value of reactive VARs was, and then use a power triangle to calculate the VA. And finally, again, another unbalanced with two resistors and an inductor, P total 27 watts, 60 VAR, and Pythagoras with power triangle determines 65.79 VA. So let's take a look at a few installations with the full process of how we go through determining all of the different values within the circuit. The first one we're going to look at is a Y unbalanced system. In a Y unbalanced system, we have 347 volts, and we've simply already filled in the wattage, the VARs, and the wattage. Now, each one of these individual loads that we see on the load side, there we go, is going to have its own individual power factor. And so load A would have a power factor of 1. and that's because it's a resistor. Load B would have a power factor of 1 because it too is a resistor. And load C would have a power factor of 0, which is meaning it lags. If we were then to calculate the entire value, well, we would take these numbers, we'd place them into a power triangle, 1200 watts of power, 600 var of reactive power, and we calculate the hypotenuse using Pythagoras. We get 1341.6 VA. Now we can also determine what the power factor is of this entire arrangement of 3 individual single-phase loads together in 3-phase. The total power factor of these loads here then ends up being 0.89. Let's take a look at another example. Same sort of process. This one we're going to calculate is going to be, again, unbalanced. So here's my unbalanced system. There's my source and load. We have 3 individual loads. Load A is a power factor of 1. Load B is a power factor of 0 lead because it's a capacitor. And load C is a power factor of 1 because it's a resistor. When we determine the total VA of this entire system, the load then exhibits a total of 1486.6 VA. And that was determined by using Pythagoras with the 1000 var and the 1100 watts. Again, the total power factor for this entire load of 3 different objects is 0.73. Well, let's try one that has no or very little information provided and see if we can't come up with a few answers. So on this system here, I provided a voltage and indicated what type of components we have on the load side, as well as how many ohms each one is represented by. The first thing I'm going to do is take this voltage and apply it to a few different places. Since it's 277 volt phase, it means that we must have a √3 relationship for the line voltage. The line voltage would be here and also here and here, but I'm just going to keep it in one place. And the way we would determine the line voltage would be to take the 277 times √3, giving us 480 volts. On the load side, the phase voltage across each one of my individual loads would again be equivalent to the phase voltage from the source. So we could take 480 and divide by √3, or we could simply take this voltage and apply it over here. So it'd be 277 volts. At this point, we can then start using some basic Ohm's law to determine what the power value is for each one, as well as the current. So Ohm's law will simply dictate that if we take the voltage and divide it by the ohms, we end up with the current. So 277 divided by 5 gives me 55.4 amps. So I'm going to enter that in. That would be for C, 55.4 amps. The next item is B, 30 ohms. Well, it's got the same voltage, 277 volts and 30 ohms. So 277 divided by 30 equals 92.33 or 9.233. So 9.23 amps. And finally, 277 divided by 20, 13.85 amps. Now it's up to us how we go about determining the total P and Q. I'm going to use the basic formula of simply taking the voltage times the current in order to determine my P and my Q. Now, the resistive value, 277 times 20, or sorry, 277 times 13.85. So 277 times 13.85 gives me 3836.45. So that would be the total watts, 3836.45 watts. The next one is the total Q. Now remember, we have capacitive and inductive, and that means that we're going to have to subtract the two. So I'm first going to do a calculation for the inductive, so L vars, and that would be 277 volts times 55.4 amps. That gives me 15,345. 0.8 var. I now am going to calculate my capacitive vars, and the capacitive vars are going to be 277 volts times the current flowing through the 30 ohm capacitor, which is IB 9.23 amps. Gives me 2,556.71. We're going to subtract the two. So 15,345.8 minus 2556.71. And I end up with 12,789.09 var. So that would be the resultant or the leftover, the remainder vars. And so we can place it up here in Q total. 12,789.09 VAR. Now the process for Pythagoras, I'm not going to write it all out. We know that Pythagoras is using the horizontal and the vertical in this situation here, and we are then going to determine the total VA. So I'm going to take my 3836.45 squared plus 12,789.09 squared, and square root the whole answer. I end up with 13,352 VA. So that's a full example of calculating everything out in an unbalanced system. Let's do another one, and we'll go a little bit quicker on this next example. Again, we have an unbalanced system. So I'm just going to start working through it, and I'm not going to describe every single step. So I know root 3 relationship, this must be 208 volts, and this must be 120 volts. 120 divided by 100 gives me 1.2 amps. 120 divided by 50 gives me 2.4 amps. And 120 divided by 35 gives me 3.42 amps. Now I'm going to work out the power. So total power, I'm going to have to add these three together. And immediately I can see that we are going to have 0 var, and that's because there is no inductive or capacitive loads. So 120 times current 1.2. It's going to add them all up. 144 watts. That would be for C. IA is 2.4 times 120. So that's 288 watts. Plus B, 3.42 times 120 volts gives me 410.4 watts, and that would be B. We add them all up. 144 plus 288 plus 410.4, I get 842.4 watts, and we know that that would also be the VA because there is no vertical component to my power triangle. Let's try another one. This time it's going to be balanced. And a balanced system is going to have identical values. And so the process becomes a lot quicker. Line voltage, root 3 larger than phase voltage, so 600 volt. We have 10 ohm resistors and 347 volt across each one. Well, basic calculation, 347 divided by 10 gives me 34.7 amps for each one of my individual loads. So each one of my lines is going to carry equal current. I also know that if I take the calculated value for one resistor, how much power it generates, then I could really just multiply it by 3. 1, 2, 3, because obviously the voltage in ohms and current will be identical for this one, and that one. So let's calculate the power of one resistor. So one load is going to be 347 volts times 34.7 amps, giving me 12,040.9 watts. If I multiply that by 3, that's going to give me the total of this entire arrangement. And that ends up being 36,122.7 watts. Now remember, we have no capacitors or inductors, so we have 0 VAR, and because we have 0 VAR, it means that the VA is going to be exactly the same value as the watts. Finally, let's do another example of balance, but this time with a different arrangement of loads. This time we're going to have a balanced delta. Now remember, delta, the voltage remains the same in phase and line. So that means 480 volts should also be present here. And 480 volts should also be present then across each one of these resistors. So first step, let's work out the current that is going to flow in each one of the phases. So the current in the phase is going to be, and I'll just put a little arrow there, 480 volts divided by 8 ohms. So 480 divided by 8 gives me 60 amps. And that would be the same for this phase as well as this phase. Now, if we want to determine the value of current that is flowing in the line, well, in delta, that would then mean that we have to increase the value of that phase current by root 3. So I line is equal to I phase times root 3. And if we have that, then it simply means we take 60 times root 3. So 60 times root 3 gives me 103.92 amps. Since all the loads are identical, each of the lines will have exactly the same value of current. Now we can definitely see that there will be 0 VARs in this system because there are no capacitors or inductors. The power total should be the value of power for one of my individual resistors multiplied by 3. So we're going to take 60 amps times 480 volts. 60 times 480 gives us a total watts for one capacitor, or one resistor rather, of 28,800 watts. I'm going to say one resistor. If we multiply this by 3, we get the total amount of power for the entire three-phase load. 86,400. 86,400 watts. And that would again be 86,400 VA because there is no vertical component to this power triangle. Now, three-phase offers some added benefits when calculating with power, especially in a balanced system. So I've shown you one method here that we can come out to totals in a three-phase load. We individually calculate the phase values, and after that we add them up, and we may or may not use Pythagoras depending if it is a resistive or something other than that load. If a three-phase system is balanced, there is a shortcut that can be used to calculate the total three-phase VA, watts, and VARs. Remember, when we say balanced, we mean each of those individual loads, so there's three of them, have the same ohms and the same power factor in each phase. So let's take a look at these new equations. So these are balanced three-phase loads power equations. The first one is this. The total VA of a three-phase load is equal to E line times I line times root 3. So we're taking the line voltage and the line current, and then because it's three-phase, we're multiplying it by the square root of 3. This is by far the most common equation that we are going to utilize. Even in the field, of all the equations, this is probably the one that would get used the most. Next one down. Well, using E line and I line and root 3, we can then multiply also by the power factor of the entire three-phase load. And when we multiply by the power factor, it gives us the total watts that our three-phase load is consuming. So E line, I line, root 3 times power factor. And finally, Q total, E line, I line, root 3, but this time I'm taking sine of the angle. So I need to know what the angle is, and I apply sine, or the trig function sine, to it. So E line times I line times root 3 times sine of the angle. Now, the first equation is, like I said, by far the one used the most. E line times I line times root 3 equals the total VA of our load. In addition to that, we can then easily transpose this equation to give us this, so line voltage if it's unknown, but more often this, the line current. If we're given the total S of the three-phase load and we know the line voltage, then we can use this equation to determine what the line current will be. Now, do the other two equations get used? They certainly do. However, most often people find it easiest to use this equation, place it into a power triangle, and then by using the power factor, quickly determine the total watts by multiplying the S total by the power factor, and then using Pythagoras to determine the Q. Now, it's certainly up to you which method you wish to use. That's simply my opinion as to what is easiest. Well, let's take a look at some examples that utilize these equations then. The first one we're going to look at is a balanced Y system. It's 208 volt, 8 amp, three-phase. Well, each one of these is identical in ohmic value, and we know that if there is 208 volts there, there's definitely 120 across each one of the resistors. What we want to look at is simply what is the total watts that this load is consuming. So, first step we're going to do is this. S total is equal to E line, I line times root 3. This gives us immediately the total three-phase load VA. If I want to know the size of each resistor now, I can take this value and divide it by 3. If I take this value and divide it by 3, this gives me 960.7 VA, and that would be the value of one individual resistor. Because there's only resistors there, we can also assume that this 960.7 is also the watts. So 960.7 watts. At this point, we could then go further and even determine the size of the resistor based on the watts and the voltage that has been applied. Let's look at another example that uses the same type of equation. This time we have a balanced delta system. Again, we have a value here of 500 VA, and it looks like if all we're given is 500 VA at a power factor of 0.6, then we should be able to work out the individual values of not only watts, but also VARs. Now, how do we come to this information down here? Well, it's actually quite a simple process. All we gave you was 500 VA with a power factor of 0.6. If we then took this and applied the zero point 0.6 to the 500 VA, we could work out what the horizontal and vertical was for this one individual leg of the delta load. Another method to look at would be simply that it is balanced, and since it's balanced, we can add the VAs directly. Now, keep in mind, this only happens if it's a fully balanced system. So since there are three, we take 500 and multiply by 3, giving us 1500 VA. We apply the power factor, and we can then determine the individual VARs and watts that this three-phase load is carrying. So because the load is balanced, the VA can be added. And it's only because it's balanced that we're able to do this. All right, well, let's take a look at another balanced example. And this time it's going to again be a delta load. So this time we're given a delta load, it's balanced, and all we're told is that it's 208 volt line and that the total watts of the load, all three added together, is 25 kilowatts. We want to know what's the phase current, the line current, what's the resistive value. So first step, let's take this equation and work out what the line current is. If I know what the line voltage and the total S of the load is, and remember it's all resistors, so S is equivalent to P, then I can calculate that it should be 69.39 amps right here. If I want to know the phase value of current, then I can take my line current and divide it by root 3, getting a smaller value. Phase current should always be smaller. If I want to calculate the resistance of the resistor, I already know that it's 208 volts applied across, and now it's simply an Ohm's law process, 208 divided by 40. Finally, how much power is each one of those individual three resistive loads actually consuming? Well, we can take our 25,000 and divide it by 3. That tells me that each one of those resistors is consuming 8,333.33 watts. We can easily prove in exactly the same way we have done here that indeed the phase current is 40 amps, and it would be by taking the phase power and dividing it by the phase voltage. And finally, Ohm's law yet again, having found the 40 amps from a different method. These two here are simply showing another way to get 40 amps and 5.2. It's simply to show that there is multiple ways that we can go about calculating these values. Now, most individual three-phase loads in the electrical industry are balanced, most of them. The only times that we really see unbalanced loads would be in things like three-phase panel boards, where we really don't have control over what is connected to each individual phase. Now, when we're given a fully balanced three-phase load, usually the nameplate will only provide two bits of information: the line current and the line voltage, sometimes horsepower and other times the total watts, but line values are the standard for the electrical industry. So if we look at two examples of common balance loads, if given this information here, we should be able to work out what the total VA is required by the motor. This is the line voltage. This is the line current. 600 times 4 times root 3 gives me 4,156 VA. If given a heater, where all we have is the voltage and the kilowatts, we should be able to work out the line current. 10,000 kilowatts divided by brackets 600 times root 3 gives me 9.62 amps.